what we call retardation effects because of the propagation of the electromagnetic fields in the vacuum. And this changes a scaling law, and now the interaction depends on minus C4 over Z4 for a ground state atom, okay? And this would be when Z is much bigger than the reduced wavelength. And the reduced wavelength the wavelength for more alkalis, just to give you an idea, would be about 1 micron. So the reduced wavelength would be something that gives you something like 100 nanometers. So this gives you an idea of what near field and what far field is in these types of interactions. Okay, some experiments, just to give you an idea of some experimental truths. So far it was theory, but then this sort of aspect of the sort of atom surface interaction was demonstrated in an experiment now in 1992 and performed in the Yale group by Ed Hines and colleagues. And in this experiment, they took sodium atoms and they passed them through a cavity. And actually, the number of atoms that actually makes it is transmitted through the cavity depends on the strength of the interaction. So what they did in this experiment is they measured the atoms that fly through, and they tried to compare the transmission, the atomic transmission, to a model, a theoretical model that they did that included the atom surface interactions. And of course, they found that actually the van der Waals interaction, or the non-retarded, the electrostatic interaction, 1 over Z3, is not compatible with the data, but the QED approach, the quantum electrodynamics approach, the quantum fluctuations approach, seems to match the data better. So this was the first demonstration, and then there were others after that. So just to give you an idea of what happens for a ground state, again, this is all for a ground state, just giving you a general introduction. I'm plotting here the shift, the energy shift for the ground state cesium atom against here a sapphire surface. And what I'm plotting here is the distance, but here what I'm plotting is not actually the energy shift, but the energy shift multiplied by Z3. And I do this just so that you can have a better inspection of the curve. So in this curve, in this graph, the van der Waals approximation would be a straight line because it's energy times Z3. So this would be minus C3. And this here, instead of a straight line, you see that you have this black line here, and this is the sort of quantum fluctuations approach. So you can actually see that it is much more, that it's a very different interaction, and it's an effect that is very important for the ground state atom. Okay, but there are not only ground state atoms, right? There are also excited state atoms, and these are quite important for us, especially if you're doing spectroscopic experiments. And in excited state atoms, there are many things that are different and that are actually very interesting. And the interesting thing about excited state atoms is, of course, the fact that they can spontaneously emit. So spontaneous emission, for example, if you take the first excited state of cesium, will couple the upper state with the downward state. And this will create a real, if you want, oscillating dipole that will be in front of the surface. So this will add an additional term in the atom surface interaction, a term of the oscillating dipole interacting with its own reflected field. And this actually will, it's a very interesting interaction because, of course, an oscillating dipole in front of a surface, as you move it away, it will come in and out of phase with his own reflected field, and this will flip the interaction from attractive to repulsive, and so on, with a period that depends on the wavelength over 2 of the transition. So actually here I plot the same graph as before, and you can see how much more exotic, if you want, the interaction of the excited state atom appears. It oscillates here a lot, and this oscillation falls much more slowly. It's a 1 over z sort of distance dependence, cos 2kz. But also, if you look at it much closer here closer to the surface, then you will find that in this regime the interaction is much more coherent with the 1 over Z3 law than the sort of ground state atom, which is here represented with the black line, which is the same line as I showed you before. So this is one of the reasons why excited states are different, and actually in our experiments we're mostly interested, and we want to demonstrate effects that are interesting and that are mostly relate to excited state atoms. Okay, what is our measurement? So our technique for measuring, one of our techniques is selective reflection spectroscopy, and the way this works is relatively simple. You have a cesium vapor cell, and this is a window, and here there's the atomic vapor, let's say cesium vapor. And what you do is you measure the reflection, the reflectivity from the window vapor interface. And this reflectivity, when you scan around the atomic resonances, will depend on vapor dispersion, so on the refractive index of the vapor, which will vary, obviously, around the atomic resonances. So these variations, you can will change the reflectivity, of course. And this will give you a signal, and it turns out that this signal is obviously sensitive to atoms that are close to the surface at a distance that is comparable to lambda over 2 pi, so a distance that's comparable to the reduced wavelength, which again is about 100 nanometers. But also, if you actually go a little bit deeper into the calculations, you find that the technique is not only sensitive to atoms that are close to the surface, but it's also sensitive to atoms that are flying parallel to the surface, and therefore they have not a velocity component in the direction of the beam. So it's not only sensitive to atoms that are close to the surface, but it's also a high resolution technique, a high frequency resolution technique, a sub-Doppler technique. So this is a good way to measure the interactions. So in our experimental protocol, what we do is we take our lasers, we scan them around a given atomic transition. We measure the experimental spectrum, the reflection spectrum, and we take this spectrum and we fit it with our models, our kind of elaborate models, and this allows us to find the C3 coefficient, like van der Waals, the van der Waals coefficient of the atom surface interaction, or more precisely, if you want, the difference between excited and ground state of the coefficients. Okay, just to give you an idea, I'm trying I will show you some spectra just to give you a better idea of how our signals look like in general. So first I will show you a signal that ignores any sort of atom surface Casimir-Polder interaction, and this would look something like this. This would be the frequency, and this would be the variation of reflectivity. And normally you would imagine some dispersive Doppler profile, but this little spike here would be an added contribution, an enhanced contribution that comes from atoms that are slow, that are flying parallel to the surface. Actually, this is a relatively small signal, but if you actually take the derivative of it by doing an FM technique, this will give you a dispersive Lorentzian profile that is actually sub-Doppler and kills this Doppler profile, and therefore it gives you a nice sub-Doppler signal. When you actually try to include Casimir-Polder interactions, you can actually see that the spectrum changes and it starts shifting towards the red, okay, but also it takes some asymmetry, and eventually if you increase the interactions, it starts becoming very much more exotic, and it's actually a good way to measure interactions, Casimir-Polder interactions. Okay, some history, like these experiments were first performed back in the 90s. Actually, I was not involved in these experiments. It was before my time. They were performed here in Paris. The first experiment was done on the first line of cesium, the first resonance of cesium, the D2 line, the 6s6p3 halves. And there was a measurement of the C3 coefficient, which was about 2 kilohertz micron cube. And then shortly after, there was the second line of cesium at blue wavelengths with a C3 coefficient of about 10 kilohertz micron cube, because it's a more excited transition. The C3 is bigger. Perhaps maybe the most interesting part about these experiments is that we have actually managed to demonstrate effects that are related to the coupling of atomic resonances with surface resonances, and this actually allows you to do some to probe some exotic regimes of the atom-surface interaction, such as repulsive regimes, or regimes that actually the interaction depends a lot on the temperature, on the actual temperature of the environment. And this is an experiment we actually published some time ago, and actually this is also done with the participation of Thierry. Okay, this is, well, a very long, probably, introduction to the subject. I will try to explain a little bit more about what we're doing now, about the experiments we're doing now, and in particular about an experiment that aims at probing Rydberg surface interactions. Okay. So Rydberg atoms are atoms that are highly excited, that have a big sort of number, principal quantum number. And when you actually increase the principal quantum number, or the effective principal quantum number, which is n star, what you end up doing is you end up increasing the atomic radius as a function of n squared. So when you increase the size as n squared, you increase the dipole moment as well, and you increase the dipole moment squared as a function of n to the fourth. And this, of course, means that the C3 coefficient is increased as n to the fourth, and this essentially gives you a strong scaling with n, and actually as you increase n, as you go towards Rydberg atoms, you actually start having huge interactions with the surface, and this is an interesting regime that we want to explore. Here, for example, if you look at the cesium-7d atom, which is the one we used to demonstrate temperature dependence, the n star would be around 4 or 5 actually, and the C3 about 50 kilohertz. And the cesium-15d that I will explore now, with an n star about 12 or 13, has an interaction of about 5 megahertz micron cube, so like 100 times bigger. And it's, of course, an object that is almost like, well, not macroscopic, that is nanoscopic now, like its radius is about 10 to 15 nanometers. So it becomes very comparable to the atom surface distance that I'm actually probing. So when this happens, there's another interesting effect, of course, that comes into play. As the atom starts blowing up and increasing in size, you can no longer assume that it's a point dipole that is away from the surface, and it becomes a bigger object. And then when this is the case, then you have to start introducing higher order interactions in order to describe the interaction between the atom and the surface. So what you have to do is to add quadruple, for example, terms, or octuple, and so on and so forth. And how would this look when you look at the energy? We said that the dipole will give you energy shifts that depend on minus C3 over Z3, and then the quadruple, for example, would give you shifts that depend on minus C5 over Z5, okay? So it's a much shorter range interactions if you want, but the C5 coefficient has a much stronger dependence on n. So as when you increase n, you essentially put yourself in a situation which is more favorable if you want to demonstrate such terms, higher order terms, that have never been experimentally explored before. So this is the idea of the experiment. This is why we think it's interesting. And before going into it, we would like to do some theory in order to have an idea what to expect for this specific atom that we were aiming at. So the difficult part is that for such atoms, there are no precision calculations of the dipole moment matrix elements that actually exist for higher lying states. But the good news is that actually these atoms, the Rydberg atoms, behave like hydrogen atoms. So actually what we can do is we can actually calculate them ourselves just by solving numerically the Schrödinger equation. So this allows us to actually measure the wave function, to calculate the wave functions. And when you have access to the wave function, you can go and measure this and calculate the C3 coefficient by calculating the average value of d squared, since you know the wave functions. All right. And this gives us a value, an estimated value, obviously, like I said before, which is faithful to the scaling law that I mentioned before, that gives you 5 megahertz micron cube. And of course, you can go and do the same for the quadruple interaction term. Now, this is much more complex, like it depends on the quadruple moment, and has a much more complex sort of functional dependence that I don't show here. But in the end, the approach is the same, and then you can actually calculate the average value of this function, and this will give you the C5 coefficient, which in the case of the 15D atom is about 2 kilohertz micron to the 5, though. So these are our theoretical estimations. Let's see what's going on with the experiments. So the experiment that we propose, that we want to do, is the following. So we have a cesium ground state atom. We pump it with a D1 strong laser, which brings it to the 6p level, the first excited level. And then we perform our selective reflection spectroscopy on the 6p15D line. So more specifically, like we aim at the F4, F3 component. These are the hyperfine, this is the hyperfine structure of cesium. We pump atoms here, but because we have a lot of collisions, actually the population is distributed between those two levels. And then when we scan our laser actually into both F3 and F4. And actually, this structure is very small to be seen. The separations are very small compared to those. So essentially, the experiment scans this and this transition. Okay, so this is how it looks like, more or less. So you have a strong, like I said, pump laser at 894 nanometers. And you have a probe laser that is, well, green or turquoise blue or green, if you want, depending on your eyes. You mix them together in a dichroic mirror, and then you have two experiments. You have the main experiment, which is the selective reflection experiment. You pass your beams, you measure the reflection, you take the reflection from the window vapor interface, and you actually measure it using an FM technique to detect it. And then here you have an auxiliary experiment that actually gives you a frequency reference in the volume of the cell. Okay, just a little bit more about how this works. This is a pump probe spectroscopy experiment in the volume. So it's a nonlinear experiment, essentially. The pump is sort of fixed at one frequency. Therefore, it pumps essentially, well, or more, one velocity class. And therefore, if you actually do simple sort of transmission experiment in this case, you actually pick up a subdoppler component. And therefore, this allows you to get a frequency reference without actually doing sort of saturated absorption spectroscopy. What is also very interesting, and we don't really know why, is that you actually pick up a subdoppler component in both these components, even the one that's populated by collisions. This is something we don't understand, but we are very glad it's there, and we can use it to get a frequency reference in the volume. So selective reflection, though, is the experiment that is interesting for me. It's not the sort of volume experiment. But selective reflection, in this case, with Rydberg atoms, is a difficult and complex experiment. So actually, to give you an idea, this is the signal that we had when we first did the experiment. So this is about 10 to the minus 6 of the atomic signal, and you have a noise here that is quite strong. You can probably guess that there is a signal, but you cannot really use this signal for extracting any measurements of the atom surface interaction. So the way to fight against noise is, of course, to sort of pay great attention to your experiment. So this is what we did. We actually controlled very well our frequency scales, our frequency references. We locked our lasers, our pump lasers, so we can have a very good control of every frequency in the setup. And what we actually did is we let the experiment run for a long time, so that this allowed us to perform integrations and overcome the noise limitations. So when we actually do all of these things, when we actually work on the experiment and improve our techniques, we pass from a signal that looks like this, or we pass to a signal that looks like this. And this is a signal that we can actually use. It looks very, very beautiful. This would be the F3 component, and this would be the F4 component. You can see here that the size of the signal, how small it is, it's like almost smaller than 1 part per million, 1 ppm, 5 to the minus 7. But here it is. It's there, and we can actually try to see how it fits with our theoretical models. So this would be our first attempt. So this is an attempt to fit our scan with our standard theoretical models that actually assume that there is a very broad, almost flat velocity distribution that is much smaller compared to the natural line width. Okay. And of course, these models, well, they're not catastrophic, obviously, but they don't fit very well. And they don't fit very well because well, in this case, you have a lot of very strong collisions inside your vapor, which gives you a big sort of collisional broadening, but also like your C3 values, like your atom surface interactions, are now so big that the van der Waals shifts become also comparable to Doppler shifts. And therefore, this model is not really the best model, and you have to actually take into account the full sort of Maxwell-Boltzmann distribution, the proper Maxwell-Boltzmann distribution, in order to get a better idea of what happens. But in the meantime, before doing this, we actually tried a simpler, an even simpler model, saying, well, since the atom surface interactions are so big, maybe we can just simply ignore the atomic motion and just assume just that the atoms are motionless. And you can actually see that this model fits much better our data, which is an indication, of course, that the C3 interactions are very, very strong, and that, well, obviously, the effects of velocity need to be taken into consideration properly. So this gives us values of the C3 coefficient that are about 6 to 10 megahertz micron cube. These are values that are slightly bigger than what we expected, which was about 5 megahertz micron cube. But in this case, of course, we are still working on our theory, and we want to properly include the effects of Maxwell-Boltzmann distribution in order to get a better measurement of the C3 coefficient. And of course, in the future, what we want is to, well, have a better interpretation of our spectra in order to extract a more accurate measurement of the C3 coefficient, and then eventually go towards higher Rydbergs, and eventually also experiments in thin cells. And we think that a much more careful analysis of our experiment can lead to a measurement of the quadrupole effects if we actually include them in our theoretical modeling. Okay, so this is the status of this experiment. And now I will change subjects a little bit. I will try to talk about molecules. Molecules are a whole different story, but they're very interesting to probe. They're much more difficult, but very interesting to probe. And this is for many reasons. One of the reasons, of course, is fundamental physics and the measurement of molecule surface interactions. Molecule surface interactions are not easily accessible with other experiments. They have been very rarely investigated experimentally, but there are some very nice sort of theoretical effects that are predicted that are sort of specific to molecules and that relate to the complex molecular geometry compared to the atomic, the simpler, much simpler atomic geometry. And these are effects that have to do with the anisotropy. This is something that we are particularly interested in, like the interaction of the molecule with the surface depends on the orientation of the molecule. But also there can be other effects that are much more difficult to probe, such as effects of chirality and so on, that have been studied experimentally. Another thing that is, of course, interesting with molecules is that they have a lot of low vibrational transitions that are scattered throughout the electromagnetic spectrum. It's almost like a frequency comb, if you want. And the interesting thing about these transitions is that you can actually use them to make frequency references. So if you actually have a compact system that has a high frequency resolution, you can have you can apply this to make a sort of frequency reference, a compact frequency reference, and this can be an interesting application for probing confined molecular gases. Okay, so the difference, of course, compared to atoms is that molecules in their low vibrational transitions have a much weaker transition probability, and they also have a partition function. They have like a lot of rotational states. So the ground state, the molecules at their sort of ground state, they are sort of repartitioned around many rotational states. And therefore, when you probe a transition, you don't access the entire population. So essentially, this is a signal problem, like you have much less signal when it comes to molecules. But what you do have an advantage of them is that they actually, you actually have very high resolution, because molecules have a very, very narrow sort of line width, natural line width, a very, very long lifetime. And this gives you a very high resolution, and essentially the broadening, the line width of the molecular transition essentially depends exclusively on the pressure broadening. So by reducing the pressure, you can just reduce the line width almost indefinitely down to about a hertz. So here we started our experiments with NH3 and SF6 molecules, and this is because actually these have the most favorable, like the strongest transitions. This is the original idea. This is why we originally started working with these molecules. The experiments look very similar. Okay, like here we have a quantum cascade laser that emits at about 10 microns. So this is like a really sort of mid-infrared, sort of very invisible wavelengths. The cells look very different. They're actually made by vacuum components, and we're actually filling them by having molecules in gas bottles. So this is much more convenient. It's a room temperature experiment. Then the ideas are the same, like you have a window and you measure the selective reflection, and you have a saturated absorption experiment, an auxiliary experiment that gives you a narrow frequency reference. But you also use here a linear absorption experiment to actually stabilize your laser and then actually scan them while they are stabilized. And this helps you a lot to reduce the frequency noise that is actually kind of important in the case of quantum cascade lasers. So when you do all this, this is actually now on the signals that we have detected some time ago. We were very happy to see them. We were not sure that we would be able to observe anything when it came down to molecules. This is why we started with relatively high pressures. You can see this is about 1 torr pressure, and you can see that in this curve you have like a relatively big line width because the pressure is big, which is almost as big as the Doppler profile. But of course, the signal is there, and we were very happy to observe it. And then, of course, what you do after that, the natural thing to do is to reduce the pressure and therefore increase the frequency resolution, because, of course, you decrease the pressure broadly. So here, for example, at 150 torr, you can see the decrease in line width. You can see that you're going towards higher resolutions, and it's at high resolutions that more interesting things can happen. So let me sort of guide you through this. Like here, for example, you have the hyperfine structure of ammonia, which is sort of relatively small. You have separations about 1 megahertz, 1 or 2 megahertz wide. And this would be a signal of about, at a pressure of about 200 millitorr. So here you're not sensitive to the hyperfine structure. You have gammas that are about 5 megahertz. And then you reduce your pressure to 75 millitorr. Here the gamma decreases and you start seeing the hyperfine structure. And eventually at 50 millitorr, you have gammas that are around 0.6 megahertz, sub-megahertz. You can see the hyperfine structure. And here we stop pretty much, because here we're actually limited by the line width of the laser that seems to be around half megahertz, 0.6 megahertz. So, but these are really interesting spectra. And then here, of course, you can see a theoretical model that does not take into account Casimir-Polder interactions, but takes into account effects that are related to laser broadening or FM broadening or everything sort of else that you can imagine. So the idea is, well, we can see that we can interpret the spectrum without interactions, but can we actually put some boundaries in the interactions? Can we actually see what happens? Can we actually use this experiment to measure interactions? And in order to do this, we can start by sort of including a high value of the C3 coefficient and looking at the spectrum. And this would, the black line again would be without interactions, and the green line would be with interactions. So you can see that this does not fit, like this value is excluded by our measurements. You can put C3 about 100 kilohertz micron cube, and this value is also excluded by our measurements, until you go down to about 10 kilohertz, probably lower than 10 kilohertz, because you can see at this point you still have differences. But this is about to the point where we set our limits, and we say that with this technique, we can actually say that the molecule surface interactions are smaller than 10 kilohertz micron cube. But of course, we need to increase a little bit our resolution in order to achieve a more precise measurement. And of course, this can be achieved by reducing the line width of the laser or by changing the rho vibrational transition and the molecule that we're actually probing. And this would be beneficial because changing lambda will actually allow you to probe molecules closer to the surface. Remember, I told you that our technique probes at distances that are lambda over 2 pi. So this is what we are. These are some things that you can think of doing in order to increase your resolution. And then, of course, you can also, what we're actually doing now is we're actually trying to identify what molecule is the most favorable for us. And we're doing calculations with our theoreticians, the collaborators, Stefan Schiel in particular in the University of Rostock in Germany. But we think that some good molecules in this case would be linear molecules such as OCS or CO2. These would have strong interactions, and these can be more easily measured with our setup. Okay, I'm talking a lot about molecule surface interactions, but I'd like to make a small parenthesis here and tell you some interesting thing we found, and we actually think that our setups can actually be used also for other interesting applications that concern molecular spectroscopy, because they can actually give information on molecular transitions. So our setup is actually a high resolution setup, so it's a sub-Doppler spectroscopy, but it's also a linear spectroscopy. So this allows you to pinpoint both transition frequencies, but also transition amplitudes. And pinpointing those two is kind of important if you want to look at the spectra of molecules. For example, CSF6 molecule is a molecule that is important for atmospheric applications, is a greenhouse molecule. So it's important to know all the transitions of the molecule and the strengths of the transitions. But this is actually not very well known if you look at the databases that exist at the moment, sort of state of the art. Really is very incomplete for many molecules, and a lot of information, more experimental information is needed to complete these databases. So in our experiment, let me show you what we've done here. The experiment is a sort of here a laser scans very wide. It's about a few hundred megahertz scan compared to a few megahertz that I showed you before in the NH3 case. So here, this is a saturated absorption setup. You can see a lot of transitions that are there for the SF6 molecule. There are narrow transitions. And here is, of course, the selective reflection spectrum. You can also see the same transitions. Now, the saturated absorption setup gives you a much better signal-to-noise ratio because it's a volume experiment, okay? But it's a non-linear experiment, so it doesn't allow you to extract information on the amplitude of the transitions. You pinpoint the frequency, but it's difficult to say something about the amplitude, whereas selective reflection, on the other hand, is a linear spectroscopy, and therefore, if you go analyze your spectra, you can fit it very closely, bit by bit, and this can give you the transition amplitudes of all the transitions of the SF6 transitions that you actually have. So just to give you an idea of why this is an interesting thing to do, I'm showing you here a simulated spectrum, the selective reflection spectrum, with all the transitions that we actually see. And these are the transitions that are actually predicted by the database. Okay, so you have a lot of transitions that are missing, and therefore our experiments can contribute something to these databases. Okay, what is the future of this experiment? And I think the future of this experiment is essentially thin cell spectroscopy. So thin cell spectroscopy thin cells are actually aimed at confining achieving a hard confinement of molecules. These will be done by sort of taking two windows, putting a spacer, and then pressing those two windows together, and then having a hole that allows molecules to come in, and you can probe them actually inside this area, whose thickness now can be micrometric or nanometric or as small as you want. So these thin cells allow you to control the thickness and therefore control the distance that the molecules have from the surface, contrary to selective reflection, where the probing depth was defined by the wavelength. So this can help you achieve much better sensitivity to Casimir-Polder interactions. So this is a good thing when you want to measure molecule surface interactions. But it's also very important because you also have the Dickey effect, which is an effect of confinement. And the Dickey effect allows you to actually have a high resolution signal, like a side Doppler signal, if the cell thickness is actually smaller than lambda over 2. And this, of course, can be very important when you're actually, if you want to fabricate compact frequency references throughout the mid-infrared using molecules as your system. Okay, just a quick presentation of where we're at so far. This is a thin cell that we've actually fabricated, whose thickness is about 5 microns, about lambda over 2, because lambda is 10 microns in the case of SF6 and NH3. And this is a signal, the signal of SF6. You can see that the signal-to-noise ratio is actually here much better because we've improved our setup and because you actually have naturally more signal with thin cells. So this is very good news for us. And then, of course, what is also good news is that we are now aiming at probing acetylene molecules, raw vibrations of acetylene that are at telecommunication wavelengths, and they allow us to actually have, they will allow us eventually to have a frequency reference that is at telecom wavelengths, which is very important for applications. So, just to summarize the thing about the thing about thin cells, so the spectroscopy of confined molecules in general. Why is it an interesting thing to do? Well, I think it's interesting because you can get information about molecular spectroscopy, about the molecules themselves. You can get information about fundamental physics and the physics of molecule surface interactions, but you can also get information. We can also use them for applications in compact frequency references based on molecules. So, well, I'm getting to the end. Thank you for your attention. And of course, I would like to thank the group, my collaborators, Biplab Dutta, who is the PhD student that works on the Rydberg project. Guadalupe Garcia Arellano is a postdoc that works on both projects. Isabelle Morin, Daniel Bloch, that are permanent members of staff and work with me, again, of course, in both projects. And some past members of our group, like João Carlos Daquinho Carvalho, who is a Brazilian that has passed from João Pessoa and has worked on both projects, both Rydberg projects and molecule projects, and of course other PhD students and master students and external collaborators that have been very helpful. So thank you for your attention, and of course, if you have any questions, please don't hesitate to ask.
So thank you very much for your presentation, Athanasios, and we are now open for questions. Alguma pergunta?
I hope I wasn't too long.
No, it's okay. Perguntas, pessoal? Okay, so I have a question.
Of course.
I remember a discussion that with molecules you could probe temperature effects for ground state molecules. Because you have many transitions that are close to the ground state. Do you intend to probe something like that?
Well, that's a good question. So the temperature effects are a little bit tricky because, of course, you need transitions with whose wavelength is not who are not very energetic, so that you can actually thermally excite. But it's also favorable if you have coupling to surface polaritons. And in the case of molecules, well, you could achieve this, you could have this, but it's a little bit complicated to do experimentally. Like you'd have to be probing at transitions that are at 10 microns. You see, you have 10 microns, you do your experiment at 10 microns, but the surface resonances are also at 10 microns, so you sort of need to find a good configuration in order to achieve it. But it's something that we're thinking about, and actually, more specifically, we're thinking about temperature effects in the lifetime. Actually, like I don't know, like if you remember, we were also talking about what about the temperature effects in the gamma that we have actually not measured with the atoms. And the temperature effects in the gamma might be interesting and much more easy to see with the molecules. This might be an interesting experiment to do. But of course, well, I mean, first we need to measure the interactions. Then we'll see about the temperature dependence.
Okay. More questions? Okay, so
yeah, I was very clear, I think.
yes, I suppose. One questions, Vitor.
So thank you very much for the talk. I will try to ask a question. So you said about that for increasing the collisions in the gas, you pass the same element to another quantum state, is something like that. So do you increase the principal number of?
Yes, I increase the principal quantum number, and we do this to measure the interactions between Rydbergs and the surface. But of course, as you increase the principal quantum number, you also have collisions of the atoms themselves. You see what I mean?
Okay. So but
yes.
how can you do it to strongly higher the principal quantum number? How do you do this in the same element?
So we just change the wavelength of our lasers, right? So we use a laser that has more energy, that has a smaller wavelength, and this sort of excites, if you want, atoms at a higher state.
Okay.
And when they go to the higher state, we measure the interaction with the surface, but there are also interactions between themselves. Is that clear? I'm not sure.
Yes, it's clear now. So thank you.
Okay, right.
And another question.
Of course, yeah.
In the SF6.
Yes, the SF6, yeah.
What kind of information can you interpret with the transition intensities of this spectrum?
So the transition intensities, actually, they are kind of important for people that do atmospheric physics, that if they want to actually measure the concentration of gases in the atmosphere, like especially greenhouse gases, like SF6 is actually in the list of greenhouse gases. It's not the most important, obviously. The most important one is CO2. But if you actually want to go and measure the concentration, it's a very, well, you actually need the transition amplitudes, the transition positions, and the amplitudes, and you actually need a higher accuracy that you would imagine. Like you probably need accuracies better than 1% in the transition strengths in order to extract accurate information about the concentrations, which are important, of course, for many applications, including maybe global warming and so on and so forth. So these are information that are interesting that you can actually access only if you have, if you know accurately the transition strengths. And for example, it's a big challenge, and there are many experiments for CO2. There are many experiments that actually aim at measuring properly the transition strengths at better than 1%, so that you can have more information of how much you actually have in the atmosphere.
Very, very interesting.
Okay.
Very interesting.
Thank you.
Thank you.
Another question?
I have one question. Can you hear me well?
Yes, I can hear you very well, yeah.
It's more an experimental question. Just you showed one spectrum very noisy, and then you said you improved with
yes. Basically, we improve it by measuring, by letting the experiment run all night.
Okay, so it was just by accumulating more time.
Pure brute force, yes.
Okay,
that's it.
okay.
Yeah. But of course, in order to be able to accumulate data, you need to have a good control of all of your setup, of the frequencies of your lasers and so on.
Yeah.
Yeah, because otherwise
you have this volume that you, I don't remember. I'm not in the optics field, but you have this reference volume that you said. This is like an internal reference that you put there to have something that varies, like with temperature and pressure of the room or something like this. Or it's something else.
No, it's actually, so what it doesn't vary. You do an experiment that allows you to identify the frequency of the transition when the atom is far away from the surface. And then you compare what you see close to the surface to what happens away from the surface. This is
okay.
This is,
now I understand. It's like your
it's
atomic reference.
Yes.
I see.
Yeah.
Okay, now I got. Thank you.
Yes.
More questions? Okay, so as usually, let's thank our presenter. Pessoal, vamos dar uma salva de palmas aí para o nosso apresentador, por gentileza. Peçam que abra o...
Thank you very much.